Next up is Stephen Olsen from going to continue a bit more about the Internet of Things and how user experience should be, I think.
That's pretty much it. We'll go through a lot of different things. We're going to start with just a little bit about me and what I do, and then how that fits in with the whole real-time operating system space, how that fits in with Qt. And with that, my name's Steve Olsen. I'm a product line manager. I work on VxWorks. I manage two things for the company. I manage our avionics software. It's built on ARINC 653. That's all about aviation safety. It's certified to the highest level of certification. And so I have that experience as well. And for general VxWorks, I work with the user interface, which includes OpenGL drivers for the hardware, interfacing with Qt to bring that on as a software solution for a full user interface, and the event handlers. So that's kind of both worlds that are hitting different aspects of pieces of the Internet of Things, as well as embedded compute. Now, some of you are going to recognize this in the room. Not all of you are going to recognize it, but this is a famous character from the movie 2001 Space Odyssey that came out in 1968. And the reason why I start with this is you say, well, what is a user interface? And if you look at this, well, this was the computer that became sentient, the HAL 9000, and in one scene, I don't want to spoil it if you haven't seen it, but in one scene, he locks out the astronaut from getting back in the ship. And he does that because he has full control of the system. So you look at an Internet of Things type application here back in 1968, there was a vision of the future in 2001 where computers became so capable that they didn't need us anymore and they saw us as a threat. But what I want you to realize is that this user interface isn't that too off, because we have interfaces. If you think about it, a lot of times art imitates forms that we already have. And in this case, form imitates art. This is the Nest. Some of you may have one in your house. Now, how sentient is it? It's a very simple user interface, and if you compare them side by side, they're actually nearly identical. So as we go through this talk, I hope that we can think about things from an Internet of Things perspective, from a real-time perspective, but as you go through your day-to-day job, as you build your user interfaces and your complex systems that are building big data analytics in there, and it's going to make decisions better than we know how to make decisions, don't make them too sentient. All right, we're going to go through a little bit of the user interface, where it's been, and talk about a few use cases. Look at embedded real-time, where VxWorks fits in the whole space of embedded, and look at some of the attributes there. We'll look at the key system specifics for safety and security, and then into the Internet of Things and how we look at the Internet of Things, where our product fits in there. And then we'll go through a couple of use cases and finally end up on an example. Now, in the past, and I'm going in the distant past, and we seem to be repeating ourselves because now we're back in the cloud, but these things, a lot of them hook to mainframes. You look at that Teletype, this is a model from 1963, but Teletypes go back to the 1930s, so it's an incredibly old, versatile technology that has stood the test of time. It's no longer in operation today, but it was your user interface. You would connect this to a mainframe, you would book time on a mainframe, you could type in your program, it would list it out there on the printer. It actually had storage too. The tape on the left side of that image coming out, that was where we stored programs. So you actually used it as a read-write storage device where you could print it out and you could feed it back in and read the program. And this was an effective method of storage. Hopefully you're not having to do that anymore. I did some, so I was right on the end of that and some punch cards. But looking at the bottom, we have the AMSI 8080, and that was famous in the movie War Games, where this kid connected into what he thought was a game computer. Turns out it was the War Games simulation computer, and it was going to start a nuclear war. Again, a sentient computer. But what I like about this is, look at the user interface. You could use this computer with nothing else. Those switches, those toggle switches, you could toggle them and set memory locations. You could set registers, depending on how you configured it. So you can use the lights on the top for an output port and actually get data back. But it's pretty crude in terms of its use, and so you had to use, most people did, use something else, which you'd find in the upper right-hand corner, the VT100, and that one was a standard for a long period of time. Started out with just ASCII, and then being able to address the screen, put in full character. It's still ASCII characters, but you could draw things with it. And we actually used terminals similar to this on the linear accelerator at Stanford. We had, believe it or not, a touch screen that was running on the LINAC, and we could control the system with user interface back in, this was the late 80s. And we had a system that was put together that I could go into any sector and start messing with the magnets or reading what was going on with some of the sensors in the system. So back there, we were starting to build user interfaces that were a little bit more intuitive. But that tells you where we were in the system. And one of the things that has happened is we've gone beyond what used to be considered a typical user interface. If you looked at the AMSI 8080, you could blink an LED, you could show a value by reading out a binary set of numbers. Not very intuitive for a user, very effective if you just want to see a bit code or a set of bits and you want to see what they're set to. But that rising floor of user interfaces, the fact that it was mentioned in the keynote, the iPhone really set the standard for new interfaces in how you interact, how people interact with them, the drive towards a touchscreen that was more intuitive. You didn't need a manual anymore. If you need a manual, then something's wrong. And if you're in an older generation, you just need a younger kid that you could hand the device to and they can pretty much figure it out. But that's the drive, is let's create user interfaces that are as intuitive as they need to be to get the job done. But spend some time in the user experience to make sure we're not overdoing some parts of the interface and making it more complex than the user is designed to handle. And other customers want that feature rich. They want to do shading. They want to rotate. They want to have an image, a 3D model of their device and float it around in space. So we've gone from blinking LEDs to creating a 3D model rendered in space and in time as it's animated through the screen. Now here's an example of some of the modern user interfaces. You can see the fridge in the center there. I don't know if any of you have an internet-connected fridge. They do exist. You can buy them. I haven't quite figured out the full use case for it, but if you want to check the weather and you're at the refrigerator, then you've got an interface for that. We talked a little bit about the Nest. The Nest is one, and I like the simplicity of the Nest, the fact that you can use a simple touch and it learns. It can connect to the internet so it knows what's going on in the weather. It can control your heating and your AC with simple relays. And then it can be set. So you start setting it at the time of day, and it learns. It learns your behaviors. It learns what you like at what time of day it is, what day of the week it is. And based on that, it's going to automatically start setting it. You're actually going to go up less and less and use the interface itself. So, and the beauty of that device is it was just purchased, that company, Nest, was purchased by Google for $3.2 billion. And this is it. Okay, it's the back-end software. It's the software running in the cloud that's enabled some of this technology. But from the user interface perspective, it's very simple, very straightforward. Your grandma can use it. And I think that it's a good example. If the iPhone, we talked about that before, it set the standard. The one on the lower right, that's the Tesla interface. And I don't have a Tesla. I have Tesla envy sometimes when I see them driving down the road in the carpool lane where they can use it as a single occupant. But the interface, I really like the interface. They took a big screen, and I drive a car that has a user interface in it. It's resistive. It's very hard to punch the codes in, and it's 2 years old, so it's not that old in terms of a user interface. It's not intuitive. I still, to this day, do not know how to delete a radio station. I don't even know how to overwrite them. If I have the same radio station in 2 locations in the list, and I might want to look at the second set, whenever I turn the car off and turn it back on, if it's on that station, it takes it to the first one in the list, and I have to scroll back down. So there's some things in the user interface that I would change today, and I haven't figured out if somebody's made an adjustment to that, make it a little bit more intuitive. But it's much better than the interfaces of the past. It can connect to my phone. I can start doing some things in terms of listening to music that I want to listen to, and set up some of that communication without having to log into my phone. And so from that perspective, I think it's done a lot. This one, with the Tesla, you see that huge display on the right-hand side. I mean, that's, I think it's a 17-inch monitor that's mounted vertically. So you get a huge piece of real estate, and it's capacitive touch. And you can use it like you would a standard tablet in a lot of ways, and bring up Google Maps, bring up your calendar for the day, push a button, and it's starting to call right from the same application. So I think they did something good with this interface, and I hope that other car companies at least replicate what they can. It's obviously a huge expense to have that big of a display, but if they could do more with capacitive touch, if they could do things a little bit more intuitively. And that's something that I hope we can all take away from this conference and from my talk today, is that we need to build systems that are intuitive, but not overly complex in the mix. All right, now if you look at this slide, these are a lot of the markets that we play in. And I would say that having a user interface that we've talked about fits in most of these. There's a couple that I would say, maybe not. But almost everyone in this screen does. And from aerospace and defense, we definitely have user interfaces running in that environment. Industrial for controlling robots, consumer electronics, transportation systems, medical devices. The two that really don't fit are energy, and you might even put the Nest there, but I really put it in consumer. And then networking, because at that point you've got a high bandwidth network connection. Why don't you just plug in and use another workstation to drive it? You don't necessarily need one on the device itself. And maybe that's a case where just a blinking LED, so when a shop worker goes by, he sees that there's a problem. But that's it. So it's a wide breadth of applications that can use a user interface. Now, when you look at these 4 different applications here, they all have some things in common. The upper left-hand corner is flying on an aircraft. The upper right-hand corner is a control station for a power generation facility. Below it is a train control operator station in a train. And the lower left is a medical, looks like a surgery room, something going on in a surgery room. People take action with life and death stakes every day, and they're doing it with embedded software. And some things are so important that they simply must work. This is the world that I deal with, certainly with the work that's going on in aircraft safety. Whenever there's an aircraft that goes down, I first think about, is that an aircraft that has our software on it? I start going through my mind, what's going on with that aircraft? Is there something that could have been caused by us? And so far, that answer's been no. We haven't had anything significant happen with any of the aircraft running our software. But it's complex software running, and we need to make sure that we do the right job there in terms of safety and security. Now let's get into the Internet of Things, and I actually call it the Internet of Important Things. And the idea that we have devices out there, and the embedded space cut its teeth on the Internet of Things before we called it that, having devices out there that could phone home if there was an internet. And even our aviation software, we had people 20 years ago where they thought there might be a problem on an aircraft that was in flight over the Atlantic, and they could log into that aircraft and get real-time statistics out of the engine in flight. So to me, that's a tremendous example of that. And a lot of aircraft use it in a big data capacity to route aircraft so that you can actually steer them around storms that may not be on the charts, or in terms of taking advantage of some of the wind conditions at different elevations. There are hundreds of aircraft flying that same route per day. Take advantage of the people that have been in front of you. Where are the turbulent areas? Where are the areas that we can catch a draft of the westerly winds, or avoid them so that we make more headway? So we've been taking advantage of this data. It's just a matter of making things that haven't been smart, haven't been connected to the internet, and making them smarter. So we look at the Internet of Things. I break it down into these essentially 5 categories, and you can break it down more than that. But if you look at the left-hand side, where we have sensors and actuators, that's the edge, what we call edge management systems. That's where you're going to have things that are interacting with the world. They're going to be sensing what's going on, maybe a temperature sensor, an actuator that's maybe a robot arm that's in motion. That's where you're doing that raw interaction with people. You move up a step, and you still have devices, and have a robot arm there where it's actually manipulating. And I see that those two left-hand side, that's really where the Internet of Things, where you interact with people more than machine, or the machine interacting with people, but it's not machine to machine necessarily. You get above that and to the right, and you're definitely dealing with machine to machine. VxWorks can play in all these areas, but I would say that its sweet spot for any real-time operating system would be those two left boxes. As you move to the right, you're getting into things that are not needing to be as deterministic, not as real-time, and your routing data. I would put, there's a cloud on the far right-hand side. That one, we typically see Linux running up there, but having communication all the way through. And there's another concept that I would put down at the gateway level that could have a local cloud. And you may have heard some people term that the fog. It's a cloud, but it's local, so it's a fog. All right. So when you get into the embedded systems, what's important to you? And if we look at these different boxes here, modular upgradable architecture, that has to deal with when you go to upgrade the system software, can you upgrade and increment it incrementally rather than taking a whole release. That's an advantage to our customers. If you think about it, when you're ready to release your product and you think there's a defect going on in a particular part, what do? Do you take a new version of the software, the complete version, or do you see, I think this is in the USB driver, let me just see if I replace that one piece with the latest driver? Or you report what you think is a defect, we verify it, we can put out a version that's been fully tested. So now when you go to release, everything else that you've been testing is still the same. It's just that one module, and you can test around that and make sure it's solid. So as a customer, you're more willing to take that patch. You need to because you're trying to solve the problem, and much more willing to rather than taking an entire distribution where something else may have changed. A scalability, so being able to run on the very edge of the Internet of Things, where you might have a small footprint, very resource constrained, and being able to run some of those same protocols and applications all the way up to a big form factor where you put in many of the different protocols that are available. Safety and security is paramount in our space, and depending on what type of devices you run, when you compare something running Linux versus something running VxWorks or another real-time operating system, we'll go and safety certify our real-time operating system, but I haven't seen to the same degree somebody doing that with Linux. So that's something to be concerned with. And virtualization, if you need to run multiple OSs and be able to configure them so that no matter what happens in certain partitions, the other partitions are safe. The highly critical ones are safe. Performance and reliability, that's always important when it must run every time. guaranteed. That's where those matter. And connectivity. You don't have an Internet of Things without connectivity. Supporting the protocols necessary to either communicate with a proprietary protocol or one of the standard protocols to connect up to whichever cloud makes sense for your application. Having those connectivity bits. And also on the other side, for devices that you need to hook up. If you want to hook up a CAN bus, an I2C bus, something across a PCI bus, having the right set of middleware so that you've got a complete solution. And a rich UI, that's where Qt comes in. Now, what do you need to do on your device? And do we have the right tools, the right toolbox so that you can get the solution? And we believe we do when we partner Qt on top of our real-time operating system. So you get a best-in-class real-time operating system with a best-in-class user interface. And then, of course, certification. If you're in a space that does certification, we've taken a lot of devices through, actually our customers have, but we've provided the evidence to come alongside our customers and help them through that process. So making sure you're sort of hitting all these things which are requirements for embedded devices. Now, I want to differentiate a little bit between what's embedded and what's general purpose. I put general purpose as your typical desktop machine. You're going to be 32 or 64-bit. We are seeing embedded with 64-bit now. That question's coming up more and more, so I believe it's here. And customers that are starting to analyze a lot of data need extra address space. Not that their programs need 64 bits, but the data set that they're analyzing needs a lot more. So this slide needs to change as well. The CPU itself, 1 to 12 cores. So actually, I think in the general purpose, we're pretty much done with 1 core. You're going to see 2 to 4 cores typical, and some of those might be hyper-threading, so you'll get an additional performance boost with that. 8 gig minimum, 64 gig. So you can scale up your memory. Where on the right side, you're running anywhere from 200K, and there you have it, 64 gig of RAM. So seeing that data set expanding on that side. Performance isn't as good, where you get 1 to 3 gigahertz on the general purpose. We're seeing embedded systems down in the 100 megahertz range, but that's compared to the old system, that 8080 we showed earlier. That was probably running at 1 megahertz. So tremendous improvement there, but nowhere near what you're getting in general purpose compute. On the left-hand side with general purpose, time is not necessarily in terms of real time, it's not a necessity. So you can scroll things off to the hard drive and essentially get unlimited address space. You can keep scrolling it off and bring it in when somebody accesses it, but typical, not used for real time. On the right-hand side, it's typical not to have a hard drive. I mean, maybe in the application you need it, but a lot of applications are running out of flash. When you run out of RAM, there's nowhere to go scroll it off to. You're not going to scroll it off. It would hurt real time. So making sure that you have that understanding there. And in terms of graphics, we see that on the left-hand side you see OpenGL as typical, and on the right-hand side we see it as well, but it's the OpenGL ES subset for the embedded systems, and also frame buffer. Some customers are happy and satisfied with a simple frame buffer user interface for being able to interact with the customer or with the user of the system. And one of the other differences is what's it designed to do. General purpose, it's meant to do whatever you need it to, highly flexible in that way, whereas the embedded system is dedicated. And the one thing that's, I think, changed in some ways is the cell phone. You go back to the early 80s and late 70s even with the Motorola cell phone that came with a big brick. It was an embedded system. It had one function, which was to make phone calls. It had an address book of 10 numbers that you could store and you could scroll through. It had a little LCD that gave you 7 digits, and so you could see most of a phone number from there. It made phone calls. And today, you look at the iPhone or an Android device, you have web access. You have texting features that are in there. You can go check your stock quotes. You can download whatever app you want. It's starting to sound more like a general purpose compute. So there's one thing that keeps it on the right-hand side, and that's connectivity. Connectivity is limited in a cell phone to just a few things. You've got Wi-Fi, Bluetooth, USB. That's it. Maybe RFID to get outside of the box. But you can't hook up an external CAN bus and do something with it. It's not designed to do that. In some cases, you might be able to use the USB as a host to pull out some data, but even that mode isn't available on all devices. So I still put it as embedded.
What about this Apple Air? It doesn't have USB, even though it has USB.
That's true. That's true. I mean, it's designed to be more of a general purpose. It doesn't have a GSM radio, at least I think not standard. It doesn't make phone calls. So I still put that over on general purpose. But I do see that cell phone itself is blending between the two so that you're getting sort of both worlds here. But you're not going to expand how much RAM is in it. In general purpose compute, as long as there's another slot, you can add RAM. Take the chip out, put another chip. You're not going to be doing that with a dedicated one. Or the Air, that one's dedicated as well. So you're right, that one's kind of blending as well. These worlds are blending. And one of the things that happens with the user interface is we're seeing the user interface expectations be the same on embedded. And you saw the horsepower difference. It's nowhere near the same capability. So we've got to be smarter about it. Good news is the screens are smaller, so it's not as much to render in real time. All right, I want to go through some definitions, and I have some slides, so this is a little bit of an eye chart, but I just wanted, so embedded, we talked about that. It's dedicated with specific applications, limited in system resources. So real time is really a combination of the next three: deterministic, preemptive, and low latency. And determinism, if the system behaves with a predetermined maximum response time, it's said to be deterministic. And the delta there is if you have a linked list of things and I have to go insert something in that list, that's indeterminate. We don't know how long that list is. So we can't tell you there's a maximum. It could be much longer or much shorter than we expect. So you have to design with determinism in mind. Preemptive, the ability for a higher priority thread to be scheduled even in the midst of a system call. So we can schedule something that's going on. And the low latency is the length of time to start processing an interrupt and actually schedule a higher priority thread. So I want to show this in a picture. To get there, I want to go through this slide, which shows you your application. And you're going to have many of these threads where you have high priority threads, medium tasks, medium priority, and low priority. And it's really what's going on in your dedicated system, how you've architected it. And you should set your priorities accordingly to your system, which is part of tuning your system to make sure it's responsive. In the real-time operating system, you're going to get timers, events, semaphores, and queues, and whatnot, all those system features that you need. And then underneath that are the ISRs. That makes up the complete system software that's running in your system and that's interfacing to the hardware. So let's go through this one application here and start with low latency. If you look at the low priority task that's running in the machine, it goes ahead and makes a system call, and during the system call, we get an interrupt. Now, you'll see that there's the first low latency block in here at the end of the system call where the interrupt came in, but it didn't actually schedule it yet. And the reason why it didn't is there are certain things that just cannot be interrupted. And so in the system call, we'll disable interrupts. Even in a multi-core system, we'll say, don't allow any interrupts, do something critical, and turn them back on. That's the first half. Then the ISR will run, so it's physically scheduled, switches over to an ISR context, runs that ISR to completion. At that point, because we interrupted the system call, we'll then go back to the system call. Now, we're still running it. Well, I thought we said we were preemptive. But there are certain times that we can handle an interrupt, but we can't handle a context switch. And if you're messing with things like context, then that's a bad time to start doing it. You might be able to take an interrupt, but you can't actually switch it. So you add up these two times, the amount of time in the system call that from the time the interrupt occurred until we actually can do the context switch, and that's that first vertical line here. That's your low latency, and so making sure that you've minimized that amount of time. If you can't, if you can't interrupt a system call, you would have had to wait till that system call completed entirely. Preemption is the other one that I talked about, and this is where we're able to take a system call. Now we're out of the critical region. We take the context switch. We now run the highest priority thread to completion. It might go into the same system call, and that's okay because we're not in a critical region. So it'll run till its completion as a higher priority task. It will always go ahead and run over a low priority task. And once it's completed, it gives up the scheduler. Now the low priority task can come in, finish the system call, and eventually start running the low priority task again. So hopefully that gives you an idea of those two attributes. The other one was just dealing with determinism. Well, if you take all those pieces in the system call and you add them together, which would have been an uninterrupted system call, determinism says that no matter what, this time might be longer than what I'm showing on the screen, but it's determined. So it could be shorter, but there's a maximum that this system call will take and no more. And this means that you know in your system, when you make a call that's deterministic, you know exactly how much time to budget for it. So if you have a system that's going to, say, scale the voltage for DVFS, where you vary the voltage and frequency, now we're scaled to a low frequency, we need to bring it back. Is there enough time to get it back in order to meet the requirements for your system design? So taking advantage of determinism in the system, you can actually calculate it because we have the numbers for our operating system, and anybody that's a real-time operating system should have these numbers, and you can use that in your system design, making sure you're always in that frame. Yes?
It looks to me at least that a high priority user space task would actually also interrupt the system call, or is it high priority task in the kernel?
That is correct. And so as you look at this page, so the question has to do with, well, we have this user task up here. It's a task, it's a high priority task. And by definition, as a higher priority, it takes precedence in the system always over the lower priority task, even if it's in a system call. System call is still determined by its maximum, but now you see the system call doesn't complete until the higher priority task, and that's okay. Because when the higher priority call does a task, it does the same system call, it's also determined. And we know that the higher priority tasks are your critical tasks. They're the ones that if you fail to complete in a certain amount of time, somebody might die. If you use that as your metric to say, my highest priority tasks in this system cannot fail, I need to respond within this window, then those are by definition, need to be the highest priority. Okay. Now, you can scale systems, and in each one of these use cases, you could use Qt with our real-time operating system. From a single function device on the left-hand side is probably the simplest. There's nothing necessarily protected in the system from the system itself. Your application could be built in with the system, and we have customers running this today. It runs out of the box. The next one over, well, okay, now we're going to run several apps. Maybe you designed some, maybe you inherited some from another group. You're not sure, you can start to protect them. Multi-tenant devices are when we actually can take applications, and once they're tested and certified, I can reuse them without changing the code. And they're a recompile if you change the architecture. If you didn't change the architecture, they're just linked to it, and you're ready to go. And they load up. So you can take advantage of different versions of your device and incrementally build them, taking advantage of some of the blocks you've built before. And then all the way to the right-hand side, where we're going to run multiple OS instances. They could be the same OS. They could be different. You could run one with your user interface, and then you use one for your real-time. And now you've divided it out. If you have enough cores in your system, then you could take advantage of the cores and split them up so they're running concurrently on your system. If you only have one core or you want to run them in different configurations, you can swap them out, and we can give you both time and space partitioning. So you meet the needs of your real time. Again, when you do time and space partitioning, you need to allocate for the time that your application's not using the CPU, making sure that you're still hitting your real time. And you take across all these different components at the bottom. So you're going to take across the security, the human machine interface with Qt, connectivity, manageability, anything from that left-hand side all the way through. All right, let's get into safety. I think the main thing that is here is that middle block of the pyramid on the left-hand side. Here you have these different specifications, these different standards by which embedded devices are measured. And we've taken our software through many different certifications with our customers. You see that second bullet, 200 customers, 350 projects, and over 70 aircraft that are using our systems. So we've done a lot of stuff to test and verify to the highest level of safety certification. But it's not just aviation, as you can see those other specs in there. We have railway customers, we have medical customers, auto customers, and industrial customers. So it's a matter of making sure you have the right safety for your domain. And we have some of the tools that will enable you to get your job done with our software. Now, there's something called multiple levels of criticality, and all that's to say is I'm going to support several different applications, some highly critical, some not so much. And you look across the top, that's the simplest case. We have a single application. It's using a single safety level, whatever level that is. You need to certify the whole system to that state, and it's going to run on a single core. That's the easiest way to look at a system, and where everybody was just a few short years ago when we were running on single core. Now that multi-cores come about, we have the complexity, and the most complex configuration is all across the bottom, where you have multiple applications, which could be written by multiple people. They need to be, they're designed for different levels of safety. So you have some highly critical, some low criticality, and they're going to run on a multi-core system. And this is the most complex. And you see the X patterns there says, well, we could have something that says it's multiple applications, but they're all at the single safety level, and they're a single core, or they're multi-core. So it goes whichever way you need it to. Just know that when you start dealing with that bottom row, the complexities of the system go exponential. And it's not trivial to go through some of these certifications. So be wary of that if you're certainly at the high end of certifiable software. All right, security. We have 4 pillars of security that we use to define systems. The first is in design. When you have your design software and you have users that are out there using your software, those users have access. Do you have a way of detecting that the system software you're getting from us, software of unknown provenance that's in your system builds, could it have been modified by one of your employees? How do you know? They had access to the system, and they can write in other places. Let's say they just decided they're going to take the TCP/IP stack and open up one of the ports. Well, if you don't know what's going on, if you don't know how it's configured, they could do that, and you'd never know. And now it's out in the field, and there's an extra TCP/IP socket open that's ready to receive a connection. Disastrous for the application. You need to make sure that your system software that's coming from a third party is what you think it is, and making sure that what you installed is still there when you go to deploy. Yeah, you might do things in development, but when you go to deploy, you need to match and make sure that nothing's changed, or if something's changed, you need to be able to explain it. So that's in development. Now at execution, the ability to sign your software. And now you establish a root of trust, and certain hardware allows you to put in a set that validates the bootloader, and then the bootloader will validate the OS, and the OS will validate the applications. As long as you have a signature root of trust all the way through to the hardware, you'll never run untrusted software. If you break that chain or choose not to put that in, you might run untrusted software. This, by the way, is one of the things that happened at the Target hack, if you're familiar with that, where they remained undetected in the system for months, just skimming off credit card data and sending it to another server. It was an untrusted boot that they booted. Somebody put in a hack, and they were able to collect that information. So Just make sure if you're building systems that need to be secure that you put in those types of capabilities. And then in operation, there's kind of two ways. One is the malicious attacks. And now that your system's out there, what kinds of holes are there in the system? And we actually get notifications from people that find holes in software. They'll notify us if they see something that's questionable in our operating system, and we have to fix it within a certain amount of time. We do get notifications from time to time. Sometimes people turn on the debug server and leave it on. So now all you have to do is have a debug client. You can connect in, you know what the port number is, you can guess it, and now you're in the system being able to control it. So making sure that you can do that. The other is when you're transmitting data, making sure you have secure links. I was using software at work one day, and I thought it was odd that the single sign-on password didn't work on this one server. And I used an old password, and I went, wait a minute. And so I put a sniffer on, and I said, here, type in, and I typed in my password, and then I saw go across the Ethernet, password, : and then there was my password right there in plain day. So I realized that there was a flaw in this one application that they did it that way. So making sure that you have security on anything that's communicating outside the device, even if it remains in the building, it can be snooped. And then at power down, I remember looking at a system that had a record that was stored, and the record was stored in a way that was unencrypted. I could actually look through, and I could see the passwords in the system, and all of a sudden I saw a password that was my password in the system. Oh. So then I just went through them, and I actually found the system installer password. That was just there stored in Flash. Very easy to find, very easy to manipulate the device at that point. And at that point, I had all the keys to that company because it was the installer code that was there as plain as day, not just our codes. So making sure you have a complete plan for security in your system. And it starts, if you look at all the pieces here, and I didn't go through them all, but certainly having the right BSP to match the hardware you're looking at, the analysis tools, so now you can start analyzing what's going on in your system. The graphics, that's certainly key, looking at Qt, and having the right pieces of safety and security. Those are the pieces that I think are paramount to the system and the connectivity as well for the Internet of Things. All right. So I want to go through some examples here, and here's one of looking at safety and accuracy. These robots are moving very fast. You're trying to keep these assembly lines moving daily. They're trying to put out as many cars or as many. The one on the left is a train car. The one on the right are automobiles. But they're trying to do the welds, do their job as fast as possible. But you could have a human that didn't know the factory floor and walked into one of these workstations. So I think this is an excellent application where you have a machine that's doing its job, but you also want to have the ability to control that machine locally, see what's going on, see the state of the machine, and maybe have a user interface so I could, as a maintenance operator, I could start to control it and use the system right there for being able to do it. It becomes an ability to control the safety of the device. And then looking at a warfare scenario, and this is one where there's many different devices. This is just representative of what's going on. And I have a story that I want to tell you about somebody that was working, and this is Desert Storm, the first Gulf War, and he was in one of the tanks that was leading the charge. And what they did is the forces that were coming across the desert towards the Iraqis, they crossed in so fast that you had a bunch of tanks intermixed, and it's night. And so you don't know who's friend and who's foe. And back then, they had an ingenious solution. And to me, I think we need the same solution, but at a higher scale. What they did is they were able to communicate securely between the tanks. And they said, okay, in 5 seconds, everyone turn on your spotlight. And so what they found is all the tanks that turned on their spotlight, those are your friends. And all the ones that had their lights out, those are your foes. And they were able to continue the battle because of that. Otherwise, you don't want to shoot your friend. You want to make sure that you're shooting the enemy. But in that scenario, you're looking at ground stations, and ground stations that need to have that capability. So we're looking at data that's being collected on each position of each tank, being set up to the cloud, and that cloud relaying enough information in a secure format back to the vehicles, the ground vehicles that you care about. And all those vehicles need to have a secure connection. They're reading that information, they're displaying it in a format so that you can actually identify, you know where you are, you know exactly where your other friends are, and you can bring that up on a display and use that to your advantage. So it's something that you might hear the term tactical cloud. So this is running literally in the fog of war to help lift that fog so that you can actually get your job done. So that's another area that I think makes sense for these types of applications. Now there's many more. I want to talk a little bit about what we've done here, and you can see this in the booth on the floor. Using the Atom X6, there's 4 Cortex-A9 cores in here. There's also a GPU, and we have an OpenGL driver that's running on there. Our operating system's running on the cores along with Qt, and we're using these standards here. You've got OpenGL ES available to you. You've got the standard shader language that's available for OpenGL ES, and it's good at 3D object manipulation. And this is where Qt fits in. You've got your user application. It can either directly render to OpenGL. If you've got something like a robot arm, you can actually instantiate its relative position. You can also use Qt to render onto that screen, either through widgets or QML, and it would take advantage of that hardware. And then, of course, the drivers around the bottom. And this is the demo that we have running on the floor. So if you look around, you'll see it. It's a medical device. It's running Qt 5.5. The software is almost released. We have testing versions of 5.5, and we're just finishing up a few things. It should officially release probably November. You take advantage of Qt Quick, and you can see the interface that's running on the left-hand side. We actually use this with an Internet of Things. So we're passing the data up to the cloud. It's coming back down through another box that you can see some of the same data. You think about having this device that's on the right-hand side. That's at a customer site or a home patient, and then the doctor's at the office. When something anomaly comes up, he can see it. All right. So we talked about several factors here. Certainly the user interface is becoming more important. Safety and security is important. And we need to balance the needs of what the embedded system's function is with the user interface. So with that, I want to turn it over to you for questions. Yes. So that's a good question. The question is, when we have the user interface, how do we keep the user interface responsive, and yet we have some real-time tasks that are running above it? And I just want to say you need to design your systems in such a way that there is enough bandwidth. And one of the things you can do, and you can do this on the Atom X6, is set core affinity. So we have the tasks that are running Qt, we can affine those to 1 or 2 cores. And then that's a quad core, we have 2 cores for your real time. We can deliver the interrupts, same thing, set a core affinity. They're only going to interrupt those cores. So now, even though it's a common operating system, we have balanced out the needs of the system. The other thing to note is that I would prefer that a system degrade the user interface, not to the point where it's gonna cause you to make a bad decision, because I think that's another case you can get to. But if all of a sudden our frame rate drops from 30 frames a second to 8 frames a second, it's gonna start to look jumpy. But you're still gonna do the real-time task, which is, if you're doing therapy on a patient, is very important. So I just keep that in mind. That's where some of the system analysis tools can come in handy to make sure that the system is balanced. All right, any other questions?
Okay, well, then thank you, and we'll be back in a few minutes with a series of very interesting lightning talks that I'm personally looking forward to. Thank you.
Thank you.